Okay, so now we're on compression and tension continuing, and we're going to talk about these two terms, buckling. What happens, or buckling, is what happens to a bridge when the compression forces overcome the bridge's ability to handle compression. So example, the crushing of a soda can or a pop can, depends on what part of the country you're from, or the United States, whether you say pop or not. Snapping is what happens to a bridge when the tension forces overcome the bridge's ability to handle tension, like the breaking of a rubber band. When building a bridge, your goal is to prevent either of these things from happening. We can do this in two ways. We can dissipate, which also means spread out the forces of transfer the force from an area of weakness to an area of strength. So, the things that you need to keep in mind when you're building your spaghetti bridge, okay, let me move this up here, are four main factors. One, your span. How long or what length is your bridge going to have? Two, the materials. Okay, now in industry, we usually use concrete, metal, stone, or wood. But for your example, you're going to use spaghetti. Three, the placement of travel surface relative to structure of the bridge. Okay, and four, the form or the shape of the bridge. So these different factors each have their strengths and they have their weaknesses. So how you combine these factors is going to depend on what exactly you need the bridge to do. You have to think about um, how many things or what are the types of vehicles that would be traveling over it. Are we talking about bikes? Are we talking about vehicles? What type of surface does it need to have? Can it be concrete? Does it need to have asphalt on it? And that's going to depend on what type of tires are rolling over it and so forth. So when we talk about the span is the length of the bridge. So the longer your bridge is, the more likely it is to start buckling. So you can see that there are different methods for creating a span that doesn't buckle. So if you look over here to your right, let me move this little recorder button. You have simple spans that are just short little sections. You have a continuous span that is one big section. We have what we call the cantilever span. That's pretty interesting. And then we also have a cantilever span that has a suspended span. Okay, fun stuff. So what I would encourage you to do is just give a real quick little drawing of these and label them as simple, continuous, cantilever span with suspended span. Then we're going to talk about what we call trusses there. So a truss is a framework. It typically consists of rafters, posts, studs, or struts that provide support to a structure. The simplest trusses are what we call the king post, and you can see over here to the right, the king post has just one support system way up at the top, okay? It's in the middle, but it's up at the top for the sides of that bridge, and then you have one span. Trusses, oh, I'm sorry, and then there's the queen post truss. So the queen post truss has two supports from the span up to the top of the truss itself. So trusses are triangles because the triangle is not easily deformed and it has the ability to balance stretching and compressive forces within the structure. Yep, triangles. Fun stuff. And so here are the many different types of trusses. Look at them, how beautiful they are. Just move this out of the way so you can look at them. Okay, you got your Pratt truss. You got your Whipple trapezoidal truss, your Parker Camelback Pratt truss, Whipple bowstring truss, multiple king post truss covered, Howe truss covered. This is like Bubba Gump shrimp. Warren truss, subdivided Warren truss, our double Warren truss, our quadrilateral Warren truss, and then our Burr arch truss that's covered. So look at all these different possibilities that you can use in making your own spaghetti bridge. It's beautiful. So trusses are bridges that are very heavy due to the massive amount of material that's involved in its construction. So in order to hold larger loads, the trusses need to be larger, but that would mean the bridge gets heavier. So eventually the bridge would be so heavy that most of the truss work is used to hold the bridge up instead of the actual load. Okay. So now we're going to talk about our travel surface placement. So we're going through all those steps of the things that you need to build a bridge. We're going through those independently. So we have our deck configuration. This is the structure that is built underneath the road and it is cross braced on the bottom. Okay, so here's a deck truss right here on the first picture to the right. Then you have what we call our pony configuration. The road is built between two parallel trusses that are not connected at the top. Okay, so it looks like it's the deck truss turned upside down, right? We have our thorough configuration or through configuration. The road is built between two parallel trusses that are cross-braced above and below the bridges. All right. And then the form. What type of form should we have? The beam or the girder? So a simple beam bridge would most likely be built using metal or reinforced concrete. Girder types are usually constructed using metal dividing the bridge into pieces and are cross-braced between two beams. So you can see that the simple beam is the first picture, and then we have our girder type is dividing the bridge into pieces. So we can see there at this bridge, I'm seeing three different pieces here. And so we have cross braces between these beams. And then we have our form. An arc bridge is the most natural of bridges. It can be designed using the deck, the pony, and the through trusses. And an arch bridge, everything is under compression, and the compression is what actually is going to hold the bridge up. How about that? It's pretty cool. So the picture shows how the compression is being dissipated all the way to the end of the bridge, where eventually all the force gets transferred to the ground. So we have different types of forms in arches. Some common examples of arches are the solid ribbed brace ribbed, which is also a truss arch, and the spandrel based. An arch bridge normally relies on vertical support to transmit the load, but some metal bridges that are spandrel based are cantilever bridges and they rely on diagonal bracing for support. So here are some arch formations. We got our solid ribbed arch, our truss deck arch, our truss through arch, our closed spandrel deck arch. So then we have our form of suspension and cable stayed. So suspension bridges, or their cousin, the cable stayed bridge, are the longest bridges in the world. The road is supported by suspenders of wire, rope, eye bars, or other types of material. So a suspension bridge uses the tension of cables to hold up a load, and the cables are kept under tension with the use of anchorages that are held firmly to the earth. So you can see our two types right here. How about that? So on forward suspension and cabled stay, the deck is suspended from the cables and the compression forces from the weight of the deck are transferred to the towers. Because the towers are firmly in earth, the force gets dissipated into the ground. So the supporting cables that are connected to the anchorages experience tension forces. The cables stretch due to the weight of the bridge as well as the load that it carries. So our support beams are our compression, and then the blue is our tension. Those are our tension wires. Continuing on with form, a cable-stayed bridge is a variation of the suspension bridge. A cable-stayed bridge uses the cable to hold up the deck. The tension forces in the cable are transferred to the towers, where the tension forces become compression forces. Uh-oh. Oops. That was an accident. All right. So this is our last slide. Um, with all cable bridges, the cables must be kept from corrosion. So the bridge is only as good as the cable. Makes sense. So if the cable snap, the bridge falls. So if the bridge needs to be longer, in most cases, the towers must also be higher. So this can be dangerous in construction as well as during windy conditions. Lots of people died making bridges back in the day. So you've already seen these pictures. So our Spaghetti Bridge project is due on the 21st of November. This is the day before we get out for, um, what is it, Thanksgiving. Yay! So we're going to be making bridges out of spaghetti and glue. You need to read the entire handout. It's got everything in it that you need to know. I can show you some examples, or I will have them sitting up. Your initial design plans are due on Monday, so you need to be making some designs using this written information down. So here's some hints. Less glue is better. It takes forever for the glue to dry, so this is a work on it a little bit at a time. Doing it up to the day it's due, not a good idea. It takes hours and hours to do. Do not wait until the night before. You're going to have a sad, sad grade and a sad, sad face. So make sure that you're doing this, and we have an accountability in the middle of it all. So on Monday, I need to know your initial plans. Now, your initial design plans may not be what you end up with, but at least you gave yourself some accountability, okay? So that is the end of today's lesson.